All right. Hello, everyone. My name is Inaya Khwaja, and I'm presenting to you from Long Island, New York. I'm currently in my second year of high school, and today I'm going to be talking to you about a study I did forecasting prospects for neutron stars via their mergers. So, I wanted to start off by introducing neutron stars and how they are created. Neutron stars are some of the densest celestial bodies in the universe, with masses comparable to the sun compressed into spheres with diameters the size of Manhattan. They were initially discovered in 1967, quite recently actually, by Dr. Jocelyn Bell, an astrophysicist at Cambridge University. Bell was actually studying radio astronomy when she first discovered the pulsing signal of a neutron star. And at first, her and her mentor marked the peculiar observation with LGM, meaning little green men, since they weren't sure of the signal's source. And later, they came the star was from a neutron star. So, how are neutron stars formed? How are they created? As shown in the evolution diagram, they are basically the remnants of a supernova explosion of a massive star. In other words, it is the last phase a star can enter in stellar evolution. These incredible explosions occur when the pressure drops just low enough in a massive star and gravity causes the core to collapse in on itself in seconds. And within the colorful haze of the supernova's aftermath, a small dense sphere packed with neutrons is left behind, and that is known as a neutron star. So now that we have some background on neutron stars, it's important to learn a bit about their mergers. Binary neutron star mergers, which I might refer to as BNS mergers, are the in-spiral and eventual collision of two neutron stars, as you can see in the image below. The reason these stars merge after a period of time is because their orbital energy is lost through occurrences like gravitational wave emission and tidal deformation. This leads to smaller and faster orbits, accelerating the merging process. Once the two neutron stars merge, there are two possible outcomes: a more massive neutron star or a black hole. And to understand why a merger ends up as one or the other, we can refer to the Tolman-Volkoff-Oppenheimer limit. So this limit determines an upper bound for the mass of neutron stars, meaning that if the mass of a neutron star exceeds that bound, it will undergo gravitational collapse. So to apply this to BNS mergers, if the resultant's mass of the merger, if its mass surpasses that limit, which is approximately 2.1 times the mass of the sun, it will collapse into a black hole. On the other hand, if it does not exceed 2.1 times the mass of the sun, the resultant will just be a more massive neutron star. Great, so now we understand neutron stars and their mergers, but how do we know all this? What signals are being emitted that allow us to comprehend such complex and extreme phenomena? And this is where multi-messenger astronomy comes in. Multi-messenger astronomy is the observation and interpretation of multiple messengers in the universe, simply put. These signals, these messengers, are emitted by powerful and energetic phenomena like BNS mergers or pulsars. They can vary along the electromagnetic spectrum, but the main four waves being observed and studied today are gravitational waves, electromagnetic radiation, neutrinos, and cosmic rays. While these have been studied for decades now, the discovery of gravitational waves, which are the ripples of the fabric of space-time, are relatively more recent. In the image, actually, the observation of waves following a binary neutron star merger was recorded over time. And you can see that the waves of this particular merger reached us and our detectors just after 100 days post the merging event. And astronomers can use this multi-messenger astronomy to combine the information and data collected from these waves and create theories about certain celestial events like neutron stars. And so recent technology has allowed us to efficiently observe and interpret these signals, specifically interferometers that can detect gravitational waves. So two popular gravitational wave detectors, LIGO and Virgo, were launched recently, relatively recently, in 1999 and 2003. And I've also added an image of LIGO on the slide. Their work has allowed astronomers to make major astrophysical advancements, such as the detection of the first binary neutron star merger, GW 170817, in the August of 2017. Furthermore, the technology has helped us understand many components of neutron stars, such as their precise masses, spins, and tidal deformability. Astrophysicists have also been able to test theories of general relativity through these interferometers from BNS mergers and other energetic events. And so today I would like to share with you all the forecast for neutron stars via the detection of multiple messengers from these mergers. Firstly, we have the composition of neutron stars. So this is a strongly theorized aspect of neutron stars, and only models have been created so far. However, as our technology advances and as our gravitational wave detectors gain more sensitivity, we should be able to approximate an accurate description of neutron star composition. It is also important to acknowledge that all neutron stars are unique and may have varying configurations. That's why astronomers should be able to study the different equation of state models on the gravitational waves emitted and determine unique levels of composition for each neutron star. So what is equation of state? The equation of state is a rule that tells you how the pressure, volume, and temperature of an object are related to each other, sort of like a recipe to describe how a substance will behave under certain conditions, but it's specific to an individual star. Next, we can learn about kilonovae and the heavy element production process. So during a BNS merger, the extreme conditions result in the R process. The R process is where atomic nuclei rapidly capture neutrons to form heavy elements and eject them. And as this neutron-rich ejecta is being synthesized, the combined emission results in a kilonovae, which is a bright blast of electromagnetic radiation. The detection of gravitational waves and their electromagnetic counterparts can help us understand more about kilonovae and why they're caused. And lastly, astrophysical jets. These are the narrow, high-speed outflow of plasma from compact objects. Astrophysical jets occur when the accumulation of matter on a compact object creates an accretion disk, which is matter orbiting an object due to gravity. I've included an image of an accretion disk surrounding a black hole. As you can see, the matter, which possesses enough rotational momentum, is in orbit around the black hole. And so going back to astrophysical jets, the magnetic field of whatever compact object is in the system, whether it's a neutron star, black hole, or white dwarf, the magnetic field of that object is theorized to play a role in forming and launching those astrophysical jets. All right, and so while we have models and possible explanations of these three aspects of neutron stars, we still have yet to learn about their specifics and how these properties can vary by certain stellar factors. So to summarize, neutron stars are the densest celestial bodies in the universe, and we have so much more to learn about them. Astronomers can use multi-messenger astronomy to combine signals from gravitational waves and electromagnetic radiation and come to conclusion about the nature of neutron stars. Since the gravitational wave signals emitted by singular neutron stars are not strong enough to be detected by gravitational wave detectors as of now, we can use the occurrence of binary neutron star mergers to learn more about neutron stars. So 3 specific aspects I explained that astronomers are currently working on are neutron star composition, kilonovae, and astrophysical jets. On a broader level, it is important to understand the properties of neutron stars because they are vital stages of stellar evolution, and their nature can help us expand our comprehension and definition of physics. Thank you for listening, and please share any questions you might have.
Thank you, Inaya, for the great presentation. Any questions from the audience? Well, I have a question for you. And you mentioned that neutron stars were discovered not so long ago, but obviously gravitational wave detectors are even more recent. So do you know how they were discovered in the first place?
Sorry, could you repeat your question? Cut out a little bit.
Yeah, so can you help us understand how neutron stars were discovered in the first place, given that gravitational wave detectors are very recent, and I assume the detection of neutron stars precedes the existence of gravitational wave detectors.
Right, so neutron stars, actually, it was a transient event of a neutron star that was discovered before we've had gravitational wave detectors. So, as I mentioned before, Dr. Bell, Jocelyn Bell, um, through her work and through after she interpreted these signals, because it was something that was never seen before, a repeating pulsing signal. So what they discovered was a pulsar, which is like a fast, rapidly rotating like, kind of neutron star. Um, and the way they found that was it was actually I'm pretty sure I'm actually not 100% sure about this, but it was through a it was kind of like a guess. So they came up with like they compared it to other signals that unknown signals that they've found from like they've observed through their work, and they compared it and they were literally saying we've never seen anything like this that's a regular repeating signal, and that's why they also denoted it like LGM because they thought it was like from maybe like an external source or like extraterrestrial. So uh, yeah, that was just through um they actually didn't come to know that it was a neutron star until the gravitational wave detectors, but they had kind of like a preconceived notion of what could be.
Got it. Thank you. And then two questions from the audience. Will our will our sun turn into a neutron star?
Will our sun turn into a neutron star? Um, you know, it is a possibility because it is a massive star, but I'm not sure how if it's massive enough to turn into a neutron star. Again, it could turn into a white dwarf. It all just depends on like the situation, the circumstance that it's in. But yeah, it is definitely a very viable possibility.
Thank you to Arshad for that question. And then we have a question from Nadim. What are the limitations of gravitational wave detectors? Is there room for advancement?
That's a great question. So this is something that's very recent gravitational wave detectors. So there is absolutely room for improvement, especially regarding the sensitivity. So as I mentioned earlier, singular neutron stars are, we don't have the ability as of now to detect a singular rotating neutron star. Um, even within our own galaxy. That's why we're using the occurrence of binary neutron star mergers or their pulsars or their magnetars. Those are just types of neutron stars that are just way more energetic. They provide stronger gravitational waves, and it's kind of more reliable data than if we saw a weak signal from a singular neutron star. So definitely, right now, astrophysicists and astronomers are working on the sensitivity of gravitational wave detectors. So yeah, it's very new and it's very, yeah, it's very.
Awesome. Thank you for the great questions, and especially thank you to Inaya for the great presentation and answers.